In an era marked by unprecedented change, equipment manufacturing has become a national priority. Today, as China undergoes comprehensive sci-tech revolution and industrial transformation, its equipment manufacturing industry, driven by innovation and supported by technological self-reliance, is shaping comprehensive new development advantages, achieving significant breakthroughs from scratch, transforming China into a manufacturing powerhouse. From this starting point, high-end equipment manufacturing with distinctive Chinese features surges ahead with formidable innovative power. A new day begins for senior technician Bai Shuhua. His task today is to weld an 800 millimeters diameter, 8-meter-long component. This is the world's largest and most challenging Hualong 1 nuclear power main pipeline. Hualong 1, China's self-developed third-generation nuclear power technology, stands as a pinnacle of global nuclear power engineering and a symbol of China's nuclear prowess. Each unit generates nearly 10 billion kilowatt-hours of electricity annually, reducing standard coal consumption by 3.12 million tons and cutting CO2 emissions by 8.16 million tons, equivalent to planting 70 million trees. Nuclear power main pipeline is the artery of a nuclear power plant responsible for transporting reactor coolant. It demands the highest standards of stability, reliability, and safety. Manufacturing such a pipeline is a global challenge. As a key player in China's fully independent nuclear technology, Bai Shuhua and his team at Erzhong Heavy Equipment have dedicated nearly a decade to continuous R&D and rigorous testing. They've mastered several proprietary technologies, successfully achieving the independent development of the third-generation nuclear power main pipeline. Not a single pinhole size defect is allowed. Welding distortion must be kept within 0.5 millimeters. The welding of the Hualong 1 nuclear main pipeline is a world-class challenge. In this critical moment, top welder Bai Shuhua must proceed with utmost care. Ultimately, with his exceptional welding skills, Bai Shuhua masterfully accomplishes yet another extreme challenge.
It requires a solid foundation of skills and the ability to accumulate experience through various structures, methods, and materials. We are honored to be part of the Hualong 1 manufacturing process, a project that boasts complete independent intellectual property. This marks China's break from foreign technology monopolies.
Since the first Hualong 1 reactor began commercial operation in 2021, we've seen a surge in large-scale engineering projects. China's third-generation nuclear technology now ranks among the world's best. With rapid strides in independent innovation and core competitiveness, China is transitioning from a follower to a leader. In key areas, Made in China is achieving groundbreaking advancements. The F-class 50 megawatts heavy-duty gas turbine, codenamed G50, is yet another marvel of China's equipment manufacturing industry. Gas turbine operates by drawing in and compressing air. The compressed air enters the combustion chamber, where it mixes with natural gas fuel and ignites, producing high-temperature gas that drives the turbine to generate immense power. As the most efficient thermal power conversion equipment, gas turbines are primarily used for power generation in gas-fired power plants. They also serve as the power heart for long-distance pipelines, aircraft, and ships. Heavy-duty gas turbine, the holy grail of the manufacturing industry, symbolizes a nation's technological prowess and overall strength. Only a handful of countries can independently develop these machines. In 2009, China's turbine manufacturers began developing the F-class 50 megawatts heavy-duty gas turbine. After over a decade, they successfully developed China's first 50 megawatts heavy-duty gas turbine, marking a significant milestone with its successful first ignition test. On the precision casting line, a unique turbine blade is being manufactured. It is one of the core high-temperature components of heavy-duty gas turbines. These turbines are categorized into E-class, F-class, and H-class, with higher temperatures indicating more advanced technology. F-class turbines operate at around 1,400 degrees Celsius, ensuring that high-temperature components function safely and reliably for tens of thousands of hours beyond the melting point of metals is a world-class R&D challenge. Turbine blades are designed to be hollow, allowing air to flow inside as they spin at high speeds for effective convection cooling. The ceramic core is crucial to the internal structure of turbine blades. Made from special ceramic materials, it can withstand temperatures up to 1,580 degrees Celsius. Through wax injection, the ceramic core is first formed into a wax mold blade. Then, an automated robotic arm evenly coats the wax mold blade with ceramic slurry and special sand, forming a ceramic shell. Under high temperature and pressure steam, the wax inside is quickly removed, leaving an empty cavity. After thorough preheating, the ceramic shell is ready for high-temperature melt casting. As 1,500 degrees Celsius nickel-based superalloy is poured into the ceramic shell, the turbine blade blank takes shape. The blade blank is then immersed in a special alkaline solution to fully dissolve the ceramic core inside. This concludes the initial manufacturing phase of the turbine blade blank. However, to achieve superior performance, it must undergo a transformation in intense heat. The spray gun ignites, producing flame exceeding 3,000 degrees Celsius. The turbine blade blank is coated with a thermal barrier layer made from ceramic and alloy powders. With its special insulating layer and its unique hollow design, the turbine blade can operate reliably in environments exceeding 1,300 degrees Celsius. For a long time, the R&D of heavy-duty gas turbine blades was dominated by foreign companies. Today, Chinese manufacturers have successfully addressed key challenges such as blade deformation, porosity, thermal crack, and core fracture. They have also established comprehensive processes and technical standards with independent intellectual property rights.
Without any equipment, instruments, or technical foundation, we had to start from scratch. Over the past decade, we've now mastered the core technologies of precision casting for turbine blades and developed the G50 blade process, breaking through bottleneck technologies and overcoming foreign blockades and monopolies.
The 50 megawatts heavy-duty gas turbine has tens of thousands of components, from technical design and materials machinery to testing facilities Each aspect is a highly complex engineering project. Developing gas turbines presents significant challenges beyond creating high-temperature components. It also requires long-term testing, verification, and accumulated experience. The full load test is about to begin. This is a crucial milestone in the development of the 50 megawatts heavy-duty gas turbine and the final performance test before its long-term operation. Isong, Deputy Director of the G50 Development Center at the Turbine Manufacturing Company, is the Chief Commander at the 50 megawatts heavy-duty gas turbine test site. Preparation is complete. All systems are now on standby.
Compressor status is normal, ready to start. Combustor status is normal, ready to start.
High-strength rotor status is normal, ready to start. Ready for ignition.
With the ignition command issued, all 8 combustion chambers of the 50 megawatts heavy-duty gas turbine ignite simultaneously. Fuel injection continues. As the load steadily increases, the turbine's speed climbs steadily, aiming for 6,000 RPM. The test team closely monitors all parameter changes. Since the first successful ignition, the 50 megawatts heavy-duty gas turbine has undergone multiple full-load tests. For the engineers, despite familiarity with each step, every test feels as critical as the first. The gas turbine is operating smoothly. Up until now, all systems have maintained stability. However, unforeseen events can still occur. 25 minutes into the operation, combustion chamber number 7 suddenly shuts down. The turbine shuts down, halting the test. It's crucial to identify the issue ASAP. As the investigation narrows, the team finds that the shutdown is caused by air mixing with the high-purity natural gas. The root of the problem lies in the aging seals of the gas pipeline valves. The team successfully resolved the issue, and the gas turbine is ready to restart.
We're now ready to restart.
72 hours later, the 50 megawatts heavy-duty gas turbine successfully completes another round of stable operation at full load. This gas turbine marks a significant leap for China in the power equipment sector. Its debut signifies a historic breakthrough, as China has developed an F-class heavy-duty gas turbine from scratch. However, the journey towards self-reliance in manufacturing remains challenging. Only by mastering key core technologies can China achieve true independence and strengthen the industry. In Hami City, Xinjiang Uyghur Autonomous Region, China's northwest, lies the northern route of the ancient Silk Road. It feels as if the sounds of caravans still echo across the vast desert. 1,000 years have passed, yet humanity's quest for the unknown remains closely tied to this historic route. Today, innovative creativity revitalizes the regions north and south of the Tian Shan Mountains, paving the way for a vibrant future. As the first light of dawn touches the horizon, Dayamahu Town awakens to a new day, along with the Super Mirror Power Plant. Up to 14,500 mirrors are arranged in an army-like circular formation. Viewed from above, they resemble a field of silver sunflowers. This is one of China's first solar thermal power demonstration projects, the Hami 50 megawatts molten salt CSP tower plant. Located east of the Tian Shan Mountains, Hami is one of China's premier solar resource regions. It receives an average total solar radiation of about 6,200 megajoules per square meter and approximately 4,000 hours of annual usable sunlight, making it ideal for solar thermal power generation. The pentagonal lizard heliostat is a core power system component, a Chinese innovation that boasts uniform load distribution, excellent stress characteristics, and high tracking accuracy. Controlled by the concentrator system, each heliostat moves in sync with the sun, automatically tracking its path with precision and continuously adjusting angles to efficiently reflect and concentrate sunlight. As the sun breaks through the clouds and rises higher, in the mirror field spanning over 1.4 million square meters, 14,500 heliostats focus sunlight onto the 181-meter-tall central receiver tower, like igniting match with a magnifying glass. Precise control of the mirror field is one of the core technologies and greatest challenges of solar thermal power generation. In the past, foreign countries kept these technical details from China. Today, Chinese equipment manufacturers have rewritten this history.
Imagine a 250-meter-long soccer field. And we're shooting at a target the size of a soccer ball. We need to hit the target with every shot, ensuring 100% perfect accuracy. This level of precision is crucial for the heliostats' tracking accuracy, ensuring they point exactly where they're supposed to.
Concentrated solar power is the process of converting sunlight into electricity. The operation of this futuristic CSP plant is actually quite straightforward. Heliostats reflect sunlight onto the central receiver tower, where the absorber at the top collects energy, heating the flowing molten salt inside to create high-temperature, high-pressure steam. That drives the turbine generator to produce electricity. Charging during the day and discharging at night is one of the remarkable features of this molten salt solar tower. During the day, sunlight heats the molten salt to generate energy, which is then stored. When the sun sets and sunlight is insufficient, the energy stored in the molten salt tanks keeps the power plant running, ensuring a seamless 24-hour power supply. The Hami 50 megawatts molten salt solar tower CSP plant is planned to have two 50 megawatts generating units. Once fully operational, it will provide the grid with 198 million kilowatt-hours of clean energy annually. This super mirror power station is a green energy engine built by China in the heart of the Gobi Desert. However, while it efficiently converts and outputs energy, it must also contend with the challenges posed by harsh natural environments.
Which stage are you cleaning today?
We're cleaning stage 14 of Group BC, from rows 48 to 59.
Alright, careful, it's a bit windy today, watch the mirrors. And maintain a safe distance for driving.
Every morning at 9 a.m., a dedicated cleaning vehicle arrives on schedule to service the 14,500 heliostats, keeping their surfaces clean. After prolonged outdoor operation, dust and dirt easily accumulate on the heliostat surfaces, reducing reflectivity and the amount of thermal energy reaching the absorber. Cleaning the mirrors is a demanding task, yet the engineers must also overcome additional challenges. Located in an arid region, the power station faces dry conditions and high salinity rainwater. Prolonged use of untreated water would not only shorten the heliostat's lifespan, but also damage the vehicle's mechanical structure and pipelines. Therefore, it's essential to use desalinated and softened water for cleaning. However, the heliostats face an even greater threat from the strong winds typical of the Gobi Desert. The maintenance has been ongoing for nearly an hour. A central axis positioning bolt broke a few days ago, severely compromising this heliostat's wind resistance. It was urgently brought in for repairs.
Now we need to use the drill bit to make a hole in this screw. Then we'll use the extractor to remove the bolt.
Luck seems to be against them. The positioning bolt broke in a tricky slot, making it hard to access with tools. Su Jie, the engineer in charge of on-site guidance, decides to handle it personally. Thanks to Su Jie's efforts, the issue is finally resolved, and the heliostat is back in operation. For over 2 years, Su Jie has been overseeing the installation, calibration, and maintenance of the heliostats, witnessing the rise of Xinjiang's first solar thermal power station.
The moment when it left the factory was unforgettable for us. We had successfully built our first heliostat. Everyone there felt like cheering.
Today, the Hami 50 megawatts molten salt solar tower CSP plant has achieved full capacity power generation. This marks China's entry into the exclusive club of countries possessing complete core technology for large-scale molten salt solar tower CSP plants. China's exploration of solar thermal power fills a gap in its clean energy landscape, providing a continuous supply of clean electricity that illuminates countless homes along this new energy Silk Road. As China accelerates toward green development, achieving dual carbon goals at high standards will be a primary focus. As a rising star in the clean energy sector, solar thermal power is set to play an increasingly vital role in this process. Skyward and seaward, traversing mountains and valleys, innovation is providing robust momentum for China's high-quality development,
which is the essential path for Chinese equipment manufacturing.
By seizing opportunities, catching up from behind, entering new arenas, and accelerating progress.
Today, China's equipment manufacturing is transitioning from quantitative accumulation
to qualitative leaps, from isolated breakthroughs to systemic capability enhancements. Technological self-reliance is propelling Chinese equipment manufacturing steadily forward.